going to talk about the invariant 2.2, which is the depth invariant. Let's review some key terms introduced before. So when we explore the concept of edge depths and how they evolve over time, each edge in our graph is assigned a depth starting at 1. These depths are crucial for maintaining certain invariants and optimizing our algorithm's performance. Let's delve into how these depths are defined and manipulated. Promotions are key in our system, allowing us to increment the depth of the, the depth of edges. This operation is not just a procedural step, it's a strategic move to ensure our algorithm remains efficient. The goal is to maintain and amortize time complexity that supports our overall performance targets. Let's see how this fits into maintaining our invariants. So the depth invariant, which is defined here, we can see that GI is a graph. It represents graph with at least depth of I. Let's just look at a definition. It includes all the vertices of the original graph, but it only includes edges which has a depth larger, no smaller than I. Okay, so every edges in GI has at least a depth of I. This is the definition. So this invariant has two property. The first one is the spanning forwards property, which is defined as the spanning forwards F is the maximum spanning forwards of G with respect to these edge depths. The second property, which will be scrutinized very in detail later, is called the weight property. So for each I, which is the depth, starting from 1 all the way to D maximum, so each connected component in GI contains at most n over 2 to the powers of I minus 1 vertices. And we will see how this will help us in maintaining the data structure in the latest slide. And this is a brief proof of why GI contains at most n over 2 to the power of I minus 1 vertices, and we will skip the proof. If you are interested, please review the slide, which we have already uploaded on the course website. Okay, let's just take as a very concrete example here. We have a graph represented by its vertices set and its edge set E here. Then we find its maximum spanning forwards F. In this case, it's a maximum spanning tree. So the vertices, the edges that is included, that is part of the maximum spanning forest, are highlighted by the red color here. Then we define vi hat as the connected component in GI plus 1. Okay, so first we review the definition. What is G1? G1 means all the vertices plus the edges that have and the edges that have at least depth of 1. Okay, so in this graph we have predefined the depth of each edges. So each edges, there is a number beside each edge. Each there are numbers beside each edges representing their depths. Okay, so in this graph, since every edge is starting at depth 1, so G1 includes all the edges. So V0 hat is the connected component in G1. So when we are looking at connected component, as we have mentioned before, when we are talking about connected component, we only look at the spanning tree. We are not looking at edges that are not in part of the spanning tree. So the connected components here is all the vertices. Okay, next. So what is V1? V1 is all the connected components that in G2. So G2 is vertices plus the edges with at least depth 2. Okay. So in the we compare these two slides, we can see that since least edge 1 is smaller than 2, so it cannot be included in the connected component. Okay. Then you may ask, okay, why this one, the edge 1 and the edge also have depth 1, but they are both included in the connected component? That's because when we are talking about connected components, we only consider edges that is part of the spanning tree. So in this case, you only need to look at the edges with the red highlight with the red color here. So there are 3 connected components in V1 hat. The first one, the second one, and the third one. And within each connected component, the edges highlighted with red are at least with a depth of 2. 3, 2, 2, 3, 2, 3, 2, 3, 2, 2, 3, and 3. Similarly, we can define V2 hat, which correspond to all the connected components in G3. And G3 means the vertices plus the edges with a depth at least 3. So we can see that the connected components within the connected components, all the red edges have a edge at least 3. So when we define V0 hat, V1 hat, we can also build a hierarchy tree or hierarchies forest here to represent, for example, the light blue connected components in V2 hat were included in the previous hierarchy in the light green connected component. So we just link the first hierarchy and the second hierarchy by their relationship in the graph. Just embed the relationship into this hierarchy, and it's quite it is quite straightforward. Okay, oh, we'll see that next. So for the last V3 hat, meaning that all the kinetic components having edges at this 4, edges having a depth at this 4, but we can see that there are no edges with depth at least 4, so no edges can be included in a kinetic component. So the result is that at the last, the maximum, which is log m, n is 15, the number of vertices, which is 3. Log 15 equals to 3, and 3 points, blah blah blah, and we take this floor of it, and it's 3. So the the bottom hierarchy is just every vertices. Okay, then we define UI is the unique I plus 1 component containing U. Okay, let's see. Again, we are using the same graph, but we only look at these vertex V8. Again, the maximum spanning forest. Again, so by definition, U subscript 0 is the unique one component containing U, and one component is a kinetic component of G1. Similarly, two components is a kinetic component of G2. So U0 is the unique one component containing U. But since there is only one component, so U0 is the whole. So we encircle it with the dark blue color. Similarly, U1 is the unique two components containing U. And the definition of two components, again, the kinetic component of G2. So there are three kinetic components of G2. This one, the second one, the third one, and which contains our V8 is the second one. So U subscript superscript 1 is the second connected component in this graph. Similarly, we can denote VU U superscript 2, which represent this connected component here. And we can also find the corresponding connected component in a hierarchy tree or hierarchy forest. So the hierarchy of the connected components is just V hat I and E hat I. So we have already defined what is the V hat I, right? It's just a kinetic component of G I plus 1. Really, I really don't know why there's a why it originally defined this way, because it really confused me when I read the paper. But maybe in the later chapter it will uh, it will be more clear why this kind of annotation were used. All right. So we have already know what is V hat I. So what about what is E hat I? Okay, let's see. So E hat I means that it is U superscript I, V superscript I for every for every edges in EI. So EI meaning that all the edges with a depth of I. Okay. So just look at the picture. So for E hat 1, meaning that every edges in with depth 1. Okay, so there are 1, 2, 3, 4, right? 4 edges. 5, 6, 4, 6 edges in E1, right? But we need to note that it has the edges, although there are 6 edges in the graph, but there are only 4 edges spanning over different. What is this? This is the connected component containing U, and this is the connected component containing V. So if you are edges between the connected component, it will be included in E1 hat. So for these two, although these two vertices have a depth of 1, but it does not span across two connected components. So these two are not included in E1 hat. So in E1 hat, there are only 4, 1, 2, 3, 4 edges. And by the definition, we know that V1 hat is just these 3 connected components. And E1 hat is the 4 edges. So we can just define a G1 hat as like a super vertex of super vertices. And if we only consider edges that is in the spanning tree, so we can just take E1 and take an intersection with the spanning tree, then we can get a spanning forest of G1 hat, right? So these are just definitions. So similarly, E2 are the set that having edges with a depth of 2. So there are 1, 2, 3, 4, 5, 6, 7, 8. 8 edges with a depth of 2, and they all happen to be spanning between two connected components. So E2 hat is just these 1, 2, 3, 4, 5, 6, 7, 8 edges. Okay, so again, we can define G2 hat in a similar manner, and we can define a spanning forest of G2 hat by only consider edges that is part of the spanning forest F. Alright. So you can see just the edges that is not part of the spanning forest were removed when we are only considering the edges in the spanning forest. It's just that simple. Okay, then we define the weight of these nodes, these large nodes, to be the number of vertices included in the nodes. So the node is just the connected component. So when we are when in the future when we talk about the weight of the connected component, it just refers to the number of vertices that are included in this connected component. So for example, what is the weight of VA2? VA2 means that the connected component of V2 hat, which includes V8. So this one, right? And this connected component has 1 and 2 vertices, so the weight is 2. So the invariant, we have already introduced the two properties. The first property is the spanning tree property, and the second is the weight property. So let's restate the weight property formally here. So the weight property from invariant 2.2 can be restated in terms of the hierarchy. The hierarchy is you can just think about a tree here, all right? The hierarchy tree. The weight of a node ui minus 1. So ui minus 1 is just the kinetic component. Let's just review the definition. Ui is the unique I plus 1 components containing U. So Ui minus 1 is the unique I components containing U. Okay, so please be careful. There is kind of an inconsistent between the superscript and the kinetic component. All right, okay. So the weight, so the restatement of this property is that the weight of the node ui minus 1 is at most n divided by 2 to the power of I minus 1. So this property ensures what? This property ensures that as we move up the hierarchy, okay, I should put the tree here. Move up the hierarchy, up. The size of the connected components become progressively smaller. Is that correct? Move up. So when we move up, okay, I mean up is when we increase I. So it's the the opposite direction in the hierarchy tree. The size of the kinetic component becomes progressively smaller, which is a key invariant that our data structure maintains to ensure efficient update and queries. And we also want to go through the concept of endpoint. So endpoint of edge E of an edge E connecting the vertex U and V is defined as the pair UE and VE. So this kind of definition has played really a crucial role when we need to sample randomly from a set of endpoints, which is a step in our later algorithm. So this sampling is done for a subset of endpoints incident to some subset V of the some subset of the subset set V. So we in this manner we treat each endpoint independently within our algorithm. This means that an edge UV with both vertices in a subset could contribute to 0, 1, or 2 endpoints to the set S. Okay? Because we treat it independently. This independent treatment allows us for greater flexibility and also precision in the algorithm processes. And this also we define what is a touch nodes. Just the an endpoint UE is touching a node if UI belongs to VI hat. Okay. So it basically means that it is associated with the connected components that contains U and at various level, okay, at various level in the hierarchy. So this concept is for all the hierarchy OI in the hierarchy and its fundamental aspect. So how we can track the connectivity relationships within the graph as it evolves. Okay, and for section 2.1, we may just skip it because it's not so crucial in this algorithm. And when we at last we are talking about some miscellaneous. Is that correct? And I don't know. Sorry. So our computation model is based on one of our steps is based on the standard. It's not standard, but in the context of our algorithm, one step we used is introduce the concept of almost uniform sampling. This means that when we sample from a set X, each element small x has a probability of being chosen that is nearly equal to the inverse of the set size, okay? Adjusted by a small factor of 1. So in our specific case, the factor is of approximately 1 over log n, and the size of x is at most a polynomial in n. So this approach ensures that all elements have a nearly equal chance of being selected, which is crucial for the fairness and effectiveness of the sampling process in the algorithm. And we will also talk about the mergeable balanced binary tree. So some part of our data structure utilize mergeable balanced binary tree, which are a type of self-adjusting tree. So these trees are designed to support efficient leaf insertion and leaf deletion operations, both of which can be performed at O log t, where t is the number of leaves in the tree. Additionally, these trees can be merged together in time proportional to the logarithm of the size of the two trees being merged. It's important to note that these trees are not used to store elements from a totally ordered set as such. They do not support a search function. This characteristic is by design, as the trees are used for structural organization rather than for element lookup. Then in next video, we will look at our algorithm at section 3.